So today we are going to be learning to understand power functions. So the main part of power functions that we're going to be looking at is understanding what does that power do to our graph. We're going to be looking at the form f of x is equal to x to the power of r, where r is a rational number. So some of the forms that we've looked at before is when we got x squared, x to the power of 4. So what we notice is both ends here are going to be going up into so it's up in the positive area and it goes straight back up into the positive area. Likewise, we've got the same thing. It's staying in the positive area. So both of these, we've got a negative gradient and then stationary point and then a positive gradient going up. The only thing you'll notice is it's a bit, the flatness is quite flat here, and then it shoots straight up a lot quicker and a lot faster than x to the power 2. And that is in relation to this power of 4. So the bigger the power of 4, the bigger this is going to be here. Now, if we've got y equals x to the power of negative 2, we've seen this function in a different way. We've seen it when last year in year 11, when we dealt with it as y equals 1 over x to the power 2. So it's just bringing to light that the power of 2 goes up to the top and it becomes a negative. Similar thing applies is the same thing. When we've got x to the power of negative 4, it's really y equals 1 over x to the power of 4, and it's the same shape that it's going to be. So we know it's always going to be in the positive area unless we've got a negative next to the 1 or next to the x squared here for it to be applied after. The ones that we've looked at before, we've looked at our basic polynomials where we know when we've got y equals x to the power of 3. Same thing, it is going to be having a stationary point right here at the origin at the moment. Same with x to the power of 5. Likewise, if we look at y equals x to the power of negative, we are able to rewrite this as y is equal to 1 over x to the power of 3. So straight away we can see, because we can't divide by 0, we already know that it's going to be some here, y equal x equals 0, and we know this is going to be an asymptote because there's nothing plus here, so there's already going to be an asymptote right here. So we know here that as our x gets bigger, our y is going to get smaller. As our x gets smaller, our y will get bigger. And it's the same way with the negatives. One of the things you'll notice here is a lot steeper rise when we've got the negative 5. Okay, so let's look at some questions now in relation to these power functions. So there's nothing new here today. It's just being able to make those connections that we've learned. So for the function g, with a rule g of x, 1 over x to the power of 3, state the maximal domain and the corresponding range. So the first thing, as I said before, we know that we cannot divide by 0. So if x is 0, there will be an asymptote. Likewise, there will be an asymptote because I'm not plussing anything. So whatever this is, when I'm dividing by 0, there's an asymptote. So it will be 0. So that gives us two asymptotes, y equals 0 and x equals 0. This defines what our range and domain can't be. It will be everything else. So our domain will be all real numbers except 0, and our range of f will be all real numbers except 0. Evaluate each of the following now. So if I've got g of 2, all I'm doing is putting 2 into my equation for x. That becomes 1 over 2 to the power of 3. 2 to the power of 3 is 8. So I've got 1 over 8. Likewise, if I've got negative 2, I'll put negative 2 in. Again, I'm timesing, going negative 2 to the power of 3, which will be negative 8. So that gives me 1 over negative. Likewise, if I put a number in that is smaller than 1, and I'm doing a half times, so half to the power 3, I'm going to get something really small. And the smaller my fraction, the smaller this is going to be here, which means 1 divided by 0.125, well, the bigger the number will be. This really tells me what my graph is going to be looking like. It's saying, I'll get, it's saying the smaller my x, the bigger my y is going to be. So straight away, if I'm going to graph this, I'm able to place this along this line right here. So I've used those 2 points to help me out. And likewise, it's hard to draw when I did it on PowerPoint, so you can probably see it's touching the line when it shouldn't. But at least it gives you a point to understand. The only thing I have not put on here is whenever we're sketching, we do need to label these couple of points, but I'm just going to put down my asymptote. What is my asymptote? If I label this, and just make sure you actually label what the asymptote is. So in this case here, my asymptote is x equals 0, y equals 0. If you've picked this point, you've got a couple points on there as your focus. You make sure that you do label them as well. So I'll just do a couple. So this one right here will be when x is a half, y is 8. And this one here would be when x is negative half, y is negative 8. And this one over here would be when x is positive 2, y is 1 over 8. And when x is negative 2, y is negative 1 over 8. Again, make sure each point you use as your key points are labeled as a coordinate. Your equations are labeled as a equation. So I've got my asymptotes right there. The next question. Let f be have a domain of all real numbers except 0. For all real numbers, f of x is equal to 1 over x to the power 3. And we've got g for all real numbers except 0. For all real numbers, g of x is equal to 1 over x to the power of 5. So the first thing, it says find the values of x for which f of x is equal to. That means I'm just grabbing this part here and this part here and equaling them together. Then I just need to get rid of the function. So I would times both sides by x to the power 5 and times both sides by x to the power 3. It instantly makes my equation x to the power of 5 equals x to the power of 3. I would take this over to the other side to make it take away, and it'll just equal 0. Next thing I'll be doing is factorizing. So that means what is common between them? They both have x to the power of 0. So my answer here, if this is 0, the whole thing is 0. Or I'm left with x squared minus 1 equals 0. So that gives me my first equation and my second one. So I take 1 to the other side and then I square root it. So we already know, if we look at our domain, x is equal 0 is not part of it, so we don't care about it. But we've got our second point. We also know that the square root will be a positive and negative. So we've got 2 points there. Now we're going to sketch the graphs of y equals f of x and y equals g of x on one set of axes. I've already graphed them, so I wanted to have all ready to show you. So what we can see here is we know where they are going to be overlapping, and I put these into these formulas. So if I just went 1 to power 3 is 1, 1 over 1 is 1. So I know on both of these, it's going to be 1, 1 is where they are overlapping. We also know, and I've color-coded this, g of x to the power of 5 is going to stay down here longer when they are less than 1, and then it's going to shoot up. When it shoots up, it will, here is where it's going to overtake, because to the power of 5, um, it's going to shoot up and get as quick as possible higher than f of x. Because the smaller our numbers here, the bigger our y will be. Then that's the same over here. A couple of functions we need to understand. Well, we know if we've got x to the power of half, we know that's a square root. So we've talked about square roots before. So that's this function right here. Likewise, if we talk about y equals x to the power of 1/4, 1/4, again, is going to be very similar. Now, if we look at 1/3, we can probably see a relationship, and this links into, gosh, this links into our graph of y equals x to the power of 3. But this is the inverse. So if we do the inverse and we switch those around and get 3 over to here, that turns into y is equal to cube root of x, which is the same as x to the power of 1/3. So just be mindful, this is an inverse of y equals x to the power of 3, which is also the reason why it's on the side here, because we know the x and y values would have switched. That's the same with y equals x to the power of 1/5. So it's a good way of visualizing so you understand where the function comes from. Okay, so we've got here that f is described by our domain is real numbers except for 0. For all real numbers, f of x is equal to x to the power of 1/4. And g is the domain is for all positive real numbers, union 0, so including 0. For all real numbers, g of x is equal to x to the power of 1/3. Okay, so again, we're going to find the values that are overlapping. So straight away, we're going to make them equaling each other. Okay. We're going to get them to one side, and we're going to take away. So we've got x to the power of 1/4, take away x to the power of 1/3. Now, it is a lot harder when we're dealing with fractions like this, so we just need to be mindful of each. Okay. So straight away, I'm going to look at what is the smallest power we have, which is 1/4. So I'm grabbing that out there. Now, this is the hard part, and I'm just going to tell you how I did it. So the first thing, if I've got this out here, what do I need to times this by to have x to the power of 1/4 there? Well, it would just be 1. Likewise, I'm going to think about what do I need to times x to the power of 1/4 by to get to x to the power of 1/12. Now I'm just going to break this part down. So we knew we were dealing with 4 and 3. So what is common between 4 and 3? It would have been 12. So I'm on the side here going to write 1/4. I'm going to make it out of 12. So that means I've got 12 there, and on top I would have had 3. So that's what x to the power of 1/4 is. We know when we are dealing with powers and we're timesing, we're just adding our powers together. So I would have had to have added a power, and that would then give me what I've got over here, which is x to the power of 1/3. So 1/3, if I rub that part out and rewrite that, we know that if I make it out of 12, it'll be 4/12. So what do I need to add to 3 to get to 4? It would have been 1/12, which is why I've got 1/12 there. Now we're able to solve. So the first part I'm going to do is solve for x. So I know the first one is x to the power of 1/4 is equal to 0, so x is equal. Now we know if we look at our domain, it's not part of our domain, so we don't worry about that. We look at the second part. we put 1 take away x to the power of 1 over 12 is equal to 0. We get our x's to one side. Now, this is the fun part. If we've got anything, if we've got sub x to the power equals 1, then our x must also, our base must be 1 as well. So that gives us our answer straight away. Now, if we are graphing to these, there's a couple of things we need to know. So we know if I look at x to the power 1 over 4, if I draw that by itself, the basic shape, we know it's going to start at 0 and go here. Normally, if I include the whole domain of x to the power of 1/3, we know um, it is the inverse of x to the power of 3. An inverse of x to the power of 3 is going to look like this on our graph. So if we be mindful of those, and we're only dealing with this from here because we're talking about um, 0 and all positive numbers, they are looking very similar. If I group them, we know that this here is going to be 1, and that's where they both intersect. The next part we need to be thinking about is what one is going to be bigger than the other. So if we can clearly see that because this is 1/4, we add to the power, we know it is going to go up a lot smaller than it would if we had 1/3, which is why you can see in the colors, the brown is going a lot quicker. The only thing I did not do is I need to make sure I label this point. You need to label everything and say coordinate, please.